Hey, morning, everyone. Thanks for coming. So, yeah, let's do the obligatory vanity slide, which I actually don't like, but it's important only because Jellyfish paid for me to be here. And this is where we built Narrow and released it. So I'll show where it's been open source. It's now an open source tool. But this came out of work that I did while supporting Cisco. All right. So this talks about software composition analysis. This might be a bad question because you chose to be in this track, but who enjoys software composition analysis? A couple hand waves is this is the best we get. I'm kind of over this topic, guys. That's kind of the truth. But every organization I go to, this is still like the top thing that we have to deal with. And then joining Cisco and now Jellyfish, it was no change there. So I was responsible for kind of supply chain security generally. Software composition analysis was one of those things. At Duo, we tried, to stay on top of every single issue. We upgraded everything. But thankfully, we also were able to do some experiments to kind of gauge to what extent findings were truly relevant to us. And so we did an experiment, and this is what we found. Less than a quarter of them were exploitable in any way. So we still ended up fixing them, but in random audits of findings, 3/4 of them we could sort of prove either through like formal methods or through human audits. That we didn't use a configuration that was a problem, or the vulnerable code path just wasn't relevant. And this was kind of discouraging. I mean, yeah, sure, it's great that we have the resources to stay on top of it, but from an investment perspective, it was kind of a bummer that we're spending all this time having engineering upgrade things, building process things to upgrade things, and still only, 1/4 of the time we're fixing anything relevant. And so, we kind of took a look at the problem. Why are we getting so many irrelevant findings? And I don't think this is a surprise. There's a lot of people are talking about it these days. Over the last 10 years, most of you have probably seen that these tools have gotten better at telling you that components you're using really are the used components. Like there was a time when you'd get half the components identified were not things you even remotely used. We're kind of past that. We verified, for instance, in that experiment, 100% of the components reported to us were in use. They just weren't vulnerable. And why is that? Well, it's usually because of a few people these days have been calling it reachability analysis, but basically you have your code calling a bunch of dependencies. And somewhere in the dependency, maybe there's a vulnerability that can be exploited in a certain situation, noted here by this red vulnerable function. But maybe your code and all the dependencies never call it. There's no actual path to it. Maybe if you were using module C, it would get called, but in this context, it never was. And this was something that in our audits we were finding happening most of the time. Most of our issues were because of this. Like if we call this particular function in a module, we would have been vulnerable, but we never did. And so the point was kind of mute. Here's like a tangible example. So here's a CVE in Twisted, Python framework. And right there in the text, it talks about how this is in the SSH client. And so if you aren't using the SSH portions of Twisted, you're almost never affected by this issue. But yet most of our vulnerability scanners will still report it to you as an issue, and you're going to have to deal with it. Now, there's been some improvements in this area, which I'm very happy about. There's kind of been this rise of using static analysis or static program analysis. So programs analyzing programs without running them to deal with some of this problem. Because the idea is if you can figure out whether you can reach the vulnerable portion of code, then you could prioritize much more effectively, and you could kind of skip having to manually audit or just upgrade everything because that's all the information you have. And so this was something we were interested in, kind of rolling out at scale, but we encountered a couple of problems with different solutions to this. And that's that they were usually quite manual. So you had what we found two primary approaches in tooling out there. One relies usually on some kind of manual rule set. So you'll build a detector that if you write it for a CVE, will help you kind of locate. You can give it to a tool and it will tell you whether that's reachable. There's the other approach, for instance, and like more common in the Go vulnerability databases, the vulnerable targets will actually be provided in the vulnerability metadata in the databases so that static analysis tools can actively use them when looking up CVEs and find paths to them. And so if you're in the Go environment, you can use like Go vuln check, and that does a nice job solving this problem. But if you're not in the situation, and that's the situation we were in, we were a mostly Python shop, where most Python CVEs have no indication of vulnerable targets one way or the other, and manual rule sets weren't covering enough CVEs, where they usually were delayed quite a bit before you'd even get something that works like that. And so we wanted to, or had a need to build a solution to this, and that is Narrow. So this is now published under the Duo Labs GitHub. It's Apache 2, so everyone's free to grab it, take a look, make improvements, suggest anything. But the big idea here is figure out what are the vulnerable portions of a vulnerability automatically, so without you having to do anything. And then do that program analysis, generate yourself a control flow graph, and figure out whether that vulnerable code can be reached by your actual first-party code base. And so the rest of the time we'll kind of talk about that and how well it behaves. All right, so first the big idea. This is kind of what we figured out after thinking about it for a while. Let's say you have a CVE and you know that there's a valid fix for it. We'll assume that there's a valid fix for the issue. The fix is going to change multiple functions in the underlying vulnerable code base. And so at least one of the changed functions has to be used in an exploit chain if an exploit were to call the code. The proof is relatively clear. If you could still do the exploit and none of the code in the fix was called, then the fix was incorrect to begin with. Minus caveats that we won't talk about right now. But in general, that's the case. And so therefore, if your program can't reach any of those modified functions, then with reasonably high certainty, the vulnerability won't actually affect you. And so our interest then was, could we automatically do that idea? Could we make use of that key idea? And we could in a lot of cases. So this is the general architecture for Narrow. Narrow takes as input some list of vulnerabilities from some other existing software composition analysis tool, a pip audit, dependency track, whatever you want. We'll talk more about input formats later. It supports different types. You can give it like GitHub security advisories. You can give it CVEs, whatever you want. Narrow will convert anything using Google's nice OSV database. If you haven't seen that, it's pretty cool to convert everything back to CVEs. And then the big idea behind Narrow is that we look up using NVD APIs get the CVE metadata, and extract from it the fixes themselves. So for now, that's like GitHub pull requests, GitHub commits. There's nothing really specific to GitHub, so this can be extended quite easily to any, fix or patch format in the future. Based on that, Narrow will extract those vulnerable targets, the things that were changed by the fix, and then it will itself perform reachability analysis on your code base and your dependencies, and then tell you if it could determine one was exploitable or not, or it didn't know. So let's real quick kind of dig into patch extraction a little bit. So here's another example CVE that's used for testing Narrow a lot. It's a request package, and this is something related to issues in handling HTTP auth headers and how they kind of handle modifying that. The details don't exactly matter, but what does matter is the list of references that are already provided by the NVD. You'll notice it has both a commit and a pull request from GitHub already included. And so our thinking was we could hopefully examine those and determine targets that we care about analyzing. So let's take a look at it. And this is what you'll get. So indeed, if you kind of follow it, on the left over there in the red is where they're changing some code relating to authorization header checks. And I kind of blew it up over here. And so Narrow will automatically examine just the diff. That's all it looks at. It doesn't compare the entire repositories at two different states. It just looks at this diff and will extract out, for instance, rebuild auth as a function of interest or a target that we might care about trying to locate. And then from that, we'll do reachability analysis on whatever you give it. All right. So here's a really trivial example of something that's could be vulnerable to this. It imports the request module and it actually makes an API request through requests with some auth information, which on response may have to call the resolve redirects and rebuild auth code. So if you run Narrow on this, you'll get something that kind of looks like this. It runs relatively quickly, less than a minute. We first, for this case, ran pip audit and just dumped out the vulnerability list in CycloneDX format. And when you run it, Narrow will find, for instance, PySec was something reported, PySec 2018-28, which is that same CVE. And it automatically pulled out those three functions as interesting targets. Rebuild auth, the one we care about, and then two test functions that won't really matter. And it will try to find a path to any of them in your code base. And sure enough, in this case, if you run it, you'll get this added metadata to your SBOM plus vulnerability output, noting that it was exploitable because it could find a code path. In fact, we have a cute little way just to print pictures of the control flow graph. This is completely unwieldy for any large code base, but it's fun for really tiny ones. That will show you paths through the code. The unknown part doesn't matter. The last number is just the argument count. But you can see in this example, it's calling like this get function, the request module, send, resolve redirects, rebuild auth, which the comments here after, if you follow the code, that's exactly the vulnerable code path in this example, which is pretty nice. And likewise, what about a case where you're not vulnerable? Let's say you're using, something like this. You're just using the request module to get, because you need some status codes. You don't actually need to make any API calls one way or the other. Most tools today are still going to report, the same CVEs because you're importing requests and you're using requests. Like, it's fair that you're using requests. You're just not using it in a vulnerable way here. So what does Narrow have to say about that? Well, once again, it'll look for the same targets, and in this case, tell you that you're not affected. I mean, there are caveats to that. We'll talk about that with the justification code not reachable. And so this was really nice for us, especially because we had a lot of CVEs to deal with where I was at. This gave us, better confidence in what to prioritize. If we had 500 things to deal with, at least we could start with things that were actually reachable. And yeah, so a lot of promise there. There are also some other kind of cute things we found that are of, would require more research, and anyways don't happen too often, but disputed CVEs, we occasionally had issues when we were fixing things that, this CVE is reported, but you go to the NVD entry and it says, this has been disputed by the vendor, and it will usually have some reason, but that's all you really get. Here are some examples of them, and here's an example of the extracted fix for, I think, the first CVE. And you'll notice it's just changing some pre-commit arguments, which likely has nothing to do with your dependency one way or the other. And so narrow would not mark you as affected by this because there's nothing really changed in the fix, which kind of got us curious. And so we audited many, I don't remember how many, maybe 20 disputed CVEs on NVD, and found that about 80% of them had no fix or valid target listed to them, which is more just interesting. It means narrow just by its nature won't really report disputed CVEs, but it could miss them. You could have valid CVEs, of course. The other 20%, there might just not be a fix added to the NVD entry. But still, it was a nice additional property that narrow had that we appreciated. All right. So I now want to kind of talk about our kind of rollout of this and some investigation we did into its efficacy. So to start out, first we did a lot of internal stuff at Cisco with pretty decent results. They were comparable to this random experiment, so I'll talk about this experiment instead. We randomly picked 3 open source repos across GitHub. The only filters we did were that it had to be a Python repo and it had to have a requirements.txt file, just for ease of implementation. We then ran pip audit on those 3 repos and collected 71 vulnerabilities. With narrow, you'll find that 21 of those had a target of some kind. So narrow was able to find a target to look for, which is roughly gives you a sense for what percentage of NVD entries you might be able to do this kind of automatic analysis on without any additional metadata. So roughly a third to a quarter. And the big thing was how many of them had no paths found. 20 of the 21. And we audited a fraction of those, I think a quarter of those, maybe half, just to verify that it was correct. And indeed, it seemed to be the case that the vast majority of the time there was no vulnerable code path, and this tool was correctly reporting that. This tool said that you were vulnerable to something only one time, which we then verified, and sure enough, yes, that one case, you were indeed vulnerable to the issue. Now I know what you're thinking. 3 repos, that's not a statistically significant result. You're so right about that. It was very time consuming to perform these audits, and so we spent more time on the implementation itself. I'd love better research to be done on this, so if you want to do more rigorous research on this methodology, feel free to talk to me. I hope we can get that published soon. But anyway, I mean, even still, these were random repos. These weren't cherry picked. And this hopefully roughly represents the scale of findings you'll get from this tool. So I mentioned specifically at Cisco, this was a big deal for us because, as you could imagine, it's a huge shop with thousands of vulnerabilities. I mean, we went in, Duo was one thing, the whole rest of Cisco product line was another thing. And so, before we might had 1,000 issues that were all marked high severity that we needed to look at. Even if we're kind of nice and say that we could fix each of those in 30 minutes, we could do an upgrade, test it, do a pull request. That was still going to give 500 hours just for this set of issues. So likely repeated many times a year, which, as you can imagine, just isn't scalable. So our approaches are usually get better at like computing risk, which is super useful, and there's a lot of great work being done there. But things like narrow are another big factor for us. So that would drop us, if you assume similar data as here, similar findings, you're going to get 20 issues of high severity that need to be prioritized, which is like 10 hours of work, which was much more scalable for us at Cisco. And indeed, this was kind of the magnitude of our reduction in findings, which was super helpful. Okay. Now, there's a trade-off here, and I think you all recognize what the trade-off is. If you compute the precision and recall values for this, again, huge parentheticals for how small this experiment was, especially on the precision side of things. The precision, but the magnitude is correct and seems roughly correct and matched our internal findings, which is why I have it here, which is that the tool is quite precise, meaning if it says something is exploitable, likely you are exploitable. So it is a good way for prioritizing findings. If you have a lot of findings to manage, this will provide value. The downside is its recall. So recall in this context would mean what percentage of vulnerabilities that are relevant to your product does it actually mark as exploitable versus what does it just miss one way or the other. And as you can see, you only get a fifth of them. So you're still missing valid vulnerabilities, and this isn't going to help you with that. So if you're able to fix everything or upgrade everything or prioritize better, you definitely would still need to do that. But that's kind of the trade-off that Narrow makes, is that it's very efficient in terms of making sure if you're going to bother fixing something, have it be something that actually reduces your risk level. But it's not complete. You're going to miss things. No argument there. Okay. And so, why is it? Why do you miss a bunch of stuff? A few reasons. Some of them can be easily improved over time. Some of them less so. Right now, one issue is just that Narrow expects a single entry point. So it is generating a control flow graph from the beginning of a program, and then we'll branch out, which works well for a lot of things, like a lot of command line tools, kind of runtime like single applications that you'd launch. But it's not going to work well, if, for instance, on API libraries. If you're writing a library, you have no single entry point. You have the number of API interfaces is your number of entry points. There's no mechanism today to say, treat all of those as an entry point and then do the analysis. However, nothing really prevents us from doing that. So maybe that's something that we could improve over time. The other kind of issue, which is inherent to this methodology, is we will generate the control flow graph completely statically for the most part. which for some languages works really well. But since I mentioned our use case was Python, and I should have said it earlier, that's what narrow does, is just Python. Python makes that tricky to do in certain situations. So that means if you're heavily reliant on kind of callbacks, especially if you do dynamic callbacks, if you're going to generate a function to call programmatically on the fly, just by statically looking at the code, we can't determine that. And so you're not going to reach paths that would have been otherwise reachable. So a lot of, for instance, if web frameworks, if you're using a web framework for your own application that does a lot of dynamic callback stuff, it tends to miss things quite often. And the last is, less easy to fix over time. Maybe the other two we can get better at. We can do some fancy stuff. But the last one is that we require Python source code. We're looking for functions in a fix. And the implementation works by having your code base and all your dependencies code bases stored somewhere. Like if you pip install them, you get a copy of all the dependency source code, which we could talk all day about whether we need to do that anyway in practice, but it is nice for narrow in that it usually works, but there are some cases where it will not work. You can pip install compiled stuff, and so you're not going to get any visibility. Narrow will just at some point have to stop tracing your control flow graph, and so again, you'll miss valid issues because of that. All right. So yeah, lots of things to do, but again, several of these we can definitely get better at over time. Some of them are kind of inherent to the methodology of choice here. Okay. And so finally, I want to talk about rolling this out, because that was all just like, okay, technically how it works, how we built it, which is fun and interesting if you like that kind of stuff. But we had some other challenges when rolling this out that might be fun to talk about. The first was modularity. So after we had this available and we wanted to roll it out to a few different product teams, we ran into some challenges in how they were implementing dependency management, and some of you likely will relate to one of these two approaches. The first was the I'm all bought into something methodology, which was the case a lot of times. This was, something like we're using vendor X basically 100%, and so our process sort of requires that we use, whatever, their services, because that's core to our how we do pull requests, how we manage findings, how we do, capture metrics. And so saying, well, how can we throw this tool in, get additional metadata, and use that in any reasonable way was a tricky conversation because there was no clear place to put anything. And so what this did is encourage us to start building, and in some cases we already had this, a more modular dependency architecture. So for instance, if you take Duo, this is closer to how it works there. There is no single tool in use. There's a bunch of code bases, and then we have there's an internal sort of orchestrator that handles parsing code bases and then can run pipelines. You can imagine this could easily be represented just as like any kind of CI architecture. Circle CI or GitHub Actions could do basically the same thing. But the big point we tried to have here are pipelines that were all generated by using well-known like standards for input and output. That was important to us, because if you don't have standard input output that you can swap in and out, you get stuck using whatever you're currently using. So here we had an architecture that was like, run any SCA tool, generate a standard SBOM format. I know we all love hearing about SBOMs, but a nice thing is there are now a lot of pretty decent standards for storing these things, which are really useful if you can actually plug and play stuff. If there's an SBOM that just is there, doesn't really help you with that much. In this case, those SBOM standards are useful because then we can insert tools like Narrow to generate, we'll say SBOM plus, but just it's the same SBOM but with more interesting information that you might care about, which is still in a compatible format, so we could pass that to a bunch of other tools if we needed to, and in some cases actually we do, but that's beyond the scope of this talk. And then finally we built there an internal reporter which did the stuff like comment on pull requests or open issues to let you know that you have a vulnerable dependency, where we would now include information from Narrow about whether you're likely to be vulnerable to something or not. So that was one big thing. We kind of recognized this need for a pipeline, and this was the encouragement to get some other teams moved over to an architecture similar. And again, you don't have to build your own cloud-based orchestrator. Just using CI in a modular way is enough to get you most of the same benefit. Another interesting problem that we had, though, was just perception in general. I see this a lot, especially when doing anything that uses program analysis, in that it can feel very hand-wavy and hard to reason about as a developer. Developers are quite used to walking through code bases and building these themselves to trace things. And so when tools come in and just claim to have done the same analysis, you very quickly become skeptical because you know all the ways that this may not work out in practice. Why in the world am I going to rely on this tool to do so? And this was no different. When we first rolled it out, it was kind of just you're vulnerable to this dependency, and we found an exploitable code path. Please fix it. And people were like, I don't trust this at all. And so when we ran surveys, the response we got was, I ignore Narrow because I don't know why it's generating output. And so they would just prioritize things like they always did, just using priority scores. And so we had to iterate on this a few times and came up with 3 properties that once implemented solve this challenge, at least in our context. The first was visualization, which I showed already, that little generated graph. We had that initially only for debugging and developing Narrow itself, but it actually became super useful when working with development teams to show why they could trust these. By having them get a copy of Narrow and be able to print out the exact control flow graph, they were much more confident in the findings presented because they had an easy way to prove it and to see the code path as it happened, versus even just initially we had just text-based output, and that was okay, but they still found it harder to use than the nice graphs. The related property, which I talked about, was that reproducibility fact. So when we just ran this in the pipeline and spat it in tickets and didn't provide any links or training on how they could run Narrow themselves, it was treated, I think rightfully, as a magic box that really shouldn't be trusted. So we spent some time making sure we had easy ways to run Narrow and to reproduce what we were running in our own environments. And that was, probably the biggest game changer, because then they could look at a few tickets, run the same thing themselves, look at the graph generated, and convince themselves that, yeah, this is reasonable. It has caveats, but this is a reasonable thing to do. And so they could start prioritizing accordingly. And follow-up survey indicated that was the case. And finally, the lack of guarantees was another thing that was important to be very clear about. Because again, I think we all know, probably all too well, a lot of tools make a lot of guarantees that really can't be trusted in any way. And so we wanted, as a security team, we wanted to be careful and not encourage blind trust of a tool. Just because we built the tool doesn't mean they should trust it any more than anything else. And so thinking critically, doing risk assessment and threat modeling was more important to us than just blindly trusting the tool. And so when we did training sessions on this tool, the tickets that were generated included comments, basically enumerating all the cases where this will not work. And that was a big deal in getting particularly developer trust boosted up by claiming that we could, if it was marked as exploitable, we wouldn't say you are vulnerable to this dependency or there is an exploit path found, because even though my nice 100% number would like to think it's not actually 100%, it's like 75 to 100 or something like that. So there were cases where it was wrong about that kind of stuff, and we want them to understand that that's a trade-off. We wanted them to understand the trade-off about missing issues. This is a prioritization mechanism. You can't just assume that because it was marked as not exploitable, that's actually true, which partly we'll talk about makes me wish there were slightly different names for some of these metadata fields, but we'll get into that. But anyway, by combining these three things together into our actual rollout, we had much higher trust and confidence, and it really enabled us to be used and not just another add-on that was largely ignored. And I think a lot of these apply to many different tools we build, and so that's the reason I throw them on here. I think that we're thinking about kind of generally. All right. The last additional problem we had was specifically the risk management case. So we have this cool metadata. We basically have now an SBOM. We all love it. We got a set of vulnerabilities that we hate, and we got now exploitability info, which is cool info. But what do you do about it now? You can put it in tickets. That's cool. But in terms of, I mentioned thousands of vulnerabilities, how are we going to start prioritizing differently just because we have this? And so we looked at a few different options. One we tried briefly was just using the info to alter CVSS scores. There was a reliance on CVSS scores, 100% recognizing all the issues with CVSS scores, and I can preach that all day long. But still, that was the process that was being used because it's relatively standardized. It's easy to understand, easy to build dashboards on, which everyone loves. And so we tried at first just taking, if you're exploitable, bump the score. If you weren't, downgrade the score. And there are nice properties with that. It's very easy to integrate. We had to change almost no process because you just kind of get, based on existing workflows, a reprioritized backlog of vulnerabilities that are roughly incorporating exploitability info, which was nice. We even exploited the exploitability modifier in CVSS, if you're familiar with that, which is usually just used to represent we know that there's an exploit available somewhere. And so you might need to look at this CVSS, weigh the CVSS a little higher. But you could also easily use that to, roughly indicate how confident you are that an exploit path exists. And that, again, does the same thing. But then you're not just artificially altering the CVSS rating down. There's some actual CVSS field that's affecting it, which was cool. Sadly, though, our rollout, we had problems with it, and for us, it was a big enough deal that we had to change it. The information loss was a big one. Which is very related to confusion. So by modifying CVSS scores, even though CVSS scores are usually meant to be used in a multiple scoring fashion. Like you can have the original CVSS and then like your assessment CVSS strictly like as a supported process. But in practice, we find it's not easily understood. It's not clear why the CVS, like we Googled this CVE and that's not the CVSS score that the web's showing. So what's going on here? So we were getting a lot of questions to that extent. And we were also, I mentioned that modular architecture, we were kind of losing our ability to build more interesting workflows after we started modifying these outputs. So the second option, which is the one we ended on, is, all right, well, let's just be straight with the fact that this is additional metadata. We just want to start using additional metadata. It's a lot clearer. It was easier for us to disambiguate cases where analysis failed. So, like again, before, if our analysis just didn't happen because there were no targets, it kind of looked like those things would all get downgraded in severity because there was no exploit available. Versus just saying, oh, we have additional metadata and it was exploitable, so we're going to change how we prioritize. This was a lot easier to do, but a little more work to integrate. We needed that modular architecture. A lot of tools, and processes do kind of assume a somewhat simple process. And so you need some freedom here to play around with. But I think it's in many cases worthwhile, especially if this is a very significant portion of your security process. How did we do that? Well, thankfully, there's a nice way to do it. You can use, in our case, we use Cyclone DX as our primary bill of materials choice. Particularly, we use the JSON representation. But they have a nice VEX capability, which for a while was like an add-on to the spec. It's now like I think 1.5 is the latest or something like that. It's a core property in the spec. This basically analysis portion over here, where you have a well-structured way to represent the state of a vulnerability, whether it's a false positive, whether you're not affected, and you can also add that justification to say like no code path available. So it did exactly the kind of stuff we needed to do, which was awesome because a lot of times you come up with a process and then you go to find the standard and you can't represent what you need to, and now you got to build another format and then get community buy-in, and it becomes a whole deal. So, in our case, this is good enough. And as such, this is the format that today Narrow takes as input. So you can give it any SBOM tool, vulnerability reporting tool output in Cyclone DX JSON format. So I mentioned pip audit is one tool that does that. Almost, many tools support such a format. And so you can take whatever tool you want, try out Narrow, gather some additional metadata, see if that helps you in your prioritization efforts. Fairly easy to do now. All right. I do also want to shout out Eclipse Steady, which I didn't know about until somewhat recently, just a few months ago. This is pretty cool. This is focused, I think, primarily on Java, at least I think it supports others too, like Python, but the Python version's more, doesn't have the same capabilities. The Java version, in many ways, is similar to Narrow in that it also has in its case, a vulnerability database, but that database is automatically generated using and includes those fixed targets as a core part of its data schema. So they have some tooling that pulls vulnerabilities, diffs the fixed version, old version, and can extract out the list of targets, throws it in the database. And then Eclipse Steady will also do program analysis, reachability analysis on Java projects when reporting vulnerabilities and dependencies, which is really nice. So you now, if you're using Java, you can use this. Python, you can try to use Narrow. So anyway, cool project. Check it out. All right. And last thing for me is call to action, because we all have an agenda. And I have an agenda, and I'm just going to tell you what it is. If you're an SCA tool builder, please consider adding reachability analysis. And if you can, even better, are there ways to make this work on, I know there are languages that are much harder, like Python, but even some support would be very appreciated over just, C and Java, because it's easier to do in that case. Well, not C, C++ maybe. But this is huge, especially for companies that have, or even just open source projects that have a lot of issues. This is a huge factor and makes these tools a lot more valuable. If you're involved in any standards for vulnerability databases, I do think it would be nice if, like the Golang world, when we report vulnerabilities, if there's an easier way to indicate what are the prerequisites or what are the targets that you need to use to be vulnerable. If we start standardizing that, you can skip half the problem with Narrow's patch extraction and just directly do program analysis, which there's a lot more literature on. So hopefully we can improve things there. And then us as kind of like users or builders of processes, implementers, and companies. Let's ask for and try to use more modular, pluggable architectures. We're doing a lot of great work building standards so that we can have tools that play well together. But if your, process implementation makes it almost impossible to input anything new, we're going to be stuck doing the same thing for a long time, especially in organizations. So consider whether you can do something a little more flexible. You might find a lot of benefit from it. All right. That's it. I appreciate you all.
Yeah, I think we have time for a brief Q&A. I think there's a mic to pass around.
You can try to say it.
Sure, yeah. So patch extraction is pretty cool. I hadn't considered that kind of from how Narrow is doing it. Just go and see, go get the methods. Have you looked at something like
Yeah. No, it's a great question. So the question was, the patch extraction part is kind of neat. Could you combine that with other tools that do specifically reachability analysis? We didn't exactly look at that because we didn't find a tool that did for Python stuff, specifically control flow through third-party dependencies well enough. But fundamentally, I think nothing stops it from happening, and I think there's there's totally a world where the patch extraction to find targets could just be its own thing that runs, and then you can use any tool that does reachability analysis to indicate whether something's exploitable. There's nothing really specific to what Narrow does versus.
So, control is interesting, but I don't know what the open source nature of it is. I think
Right. Yes, and that was also in our case. We had a lot of commercial code, so yeah, it wasn't an option. But for open source, it could be totally. Same with I think there are many others tools out there that would work fine. Cool. Yeah, totally. Thanks. I think right there.
You didn't mention the transient word, as I recall. Does it support transient dependencies? And I guess, as you understand it, if you're given the starting point and the source code for all the dependencies, which Python dependency tree is typically 4 deep, would it handle reachability for transient dependencies?
Yeah, great question. So works generally fine. Transients handled largely without issue. Again, minus the caveats that if a dependency doesn't have source, it'll stop there, but it'll follow through all code paths, including transient. Yep.
Second question. Once you put the output into your Cyclone, DX, etc., how, from a developer point of view, do you unify the experiences? And developers will be working in whatever interface of choice, GitHub or IDE. How do you give them a unified view? As in, one tool is saying you're vulnerable somewhere far away over here. It's saying you're not. How do you reconcile that so that they get the one unified view across the developer tools and experience?
Yeah, totally. So that's where that modular architecture point came in. For some of our teams, we never could, not easily, because, for instance, if they're bought into GitHub Security's interface for managing dependencies, there wasn't really a great way to indicate exploitability info in anything. So for us, it was that like orchestrator where we control developer workflows, which I understand not every organization can spend effort on such a process. But for us, that's how it worked, is we would run all the SCA tools, and then we, would create our own tickets or open our own pull requests or create our own comments on issues, on pull requests, so that they do get that unified experience. And then also we could easily like swap out SCA tools or vendors when we wanted without disrupting the flow. But if you don't have that, then the thing we did do for those teams that were stuck is we used our orchestrator basically only in an observe mode where we would capture the data just from a like reporting perspective, because we wanted them to be fairly understood in comparison to their peer teams. If we were prioritizing peer teams based on this additional metadata, we wanted to make sure that, like for instance, executive reporting, they had the same advantage basically to downplay issues. But that was it.
Thank you.
Yeah, thank you.
So just one question about the patch extraction. Did you run into problems where developers would typically squash like a set of commits into one commit, and then basically the security fix would be bundled in with lots of other like bug fixes of various kinds?
Yeah, that's a great question. Not often, I want to say. Like, for instance, meaning in our like random audits when we were doing testing, I want to say that only happened once. Not saying it doesn't happen. Usually it does. The one time we saw it, it like squashed a whole bunch of unrelated commits into it. Actually, it still worked okay because the vulnerable function was still found, and so it still predicted the path, even though there was extra stuff also in there. But I would imagine that every now and then you'll run into cases where that happens and you get some ambiguous responses where it will say you are vulnerable and maybe you aren't. But it didn't happen too often, I guess. But again, I think more research is probably needed for strong claims on that.
Just one more comment. Maybe that getting more statistics, that could be like a good student project for someone to do.
Yeah. No, I think there's a lot of cool things here that would lend themselves to research, and yeah, for anyone, a student or anyone academically inclined, I think there's some cool data that we could get published out there. Better than my colloquial examples. Maybe last one.
So for CVEs where you don't have a specific commit reference, where you don't have a target defined, would it be possible to look at, say, the diff between the last vulnerable version and the first fixed version and use that as a basis for, the fix must be in there somewhere. Maybe it's not specifically pointed out, but is that something that the tool would support? Is that something the tool could cope with, or would it be potentially too much code? Yeah,
that's a good question. And that's kind of, I guess, from my understanding, that's like the Eclipse Steady project's approach. So I think the idea would work fine. For narrow, it's possibly, I don't know. The design trade-off is we want narrow to be relatively fast to run, and we don't want it to require any external services other than like OSV and NVD. But we don't want organizations to have to deploy any additional stuff. So if that diff could be done fast enough, I think it'd be a fine thing to incorporate. If that adds too much runtime slowness, though, it might be better to treat it as like a separate project that you could choose to use or not.
Just to be clear, that the time it would take is based on the control flow analysis to arrive to all different places, or the time taken to generate the diff in the first place?
Either one. My only concern would be if the diff portion takes too long, like for large code bases, but I don't have any data to know how long it would take to do. Probably.
You know, the diff would just have to happen once in principle, as in once you've got a CVE and you know, okay, it's from version 1.12 to 1.13, you generate the diff between those two, then that diff is always that diff. And it doesn't matter how many times you run narrow, the diff should be the same thing, right? And then it's just a question of figuring out, do I arrive at that diff or not?
Right. Yes, exactly. And that's kind of the same thing. Like even here, when we pull, we generate a control flow graph, once, and then all CVEs are checked against the same control flow graph. You could do the same thing. Totally fine. Yeah. As long as, again, the only thing is because we're not storing metadata, we're not caching metadata anywhere, like on a remote server, every user, when you run it, would have to generate the diff, which is a little wasteful. But again, if you can run it on your machine fast enough, why not? So, yeah, great idea. Cool.
All right, I think we're at time. Thanks, Josiah. Let's give a round of applause.